Let's start a new topic, geometrical optics. In this topic of geometrical optics, we'll be learning about light. What exactly light is in terms of the geometry of path of light. When I say geometrical optics, geometry of path of a light, what does these things actually mean? Okay, before I tell you anything further, optics, essentially geometrical optics or wave optics, is a very boring chapter if you take my word of it. But the idea here is to make it interesting. Let me tell you a story. Once what happened was, I'm drifting apart, rather I'm slightly digressing, but let's bear with it right now. What happened was, I was having my lunch and there was a salt dispensing thing. And all of that salt dispensing thing was not working properly. So all the salt of it came on my plate and it was fully spoiled. It was very salty and almost like poison. So you could not eat that food. That was totally excess of salt. But I took it as a challenge that let's go through it, let's finish it off. But what happened later was, gradually the taste built on itself. It tasted okay after a while. And after I completed the last morsel, I was done with it. And I felt happy about it, that this thing has been accomplished. So let's read geometrical optics with this idea in mind, that I know this is boring. It's not that interesting like mechanics or thermodynamics or magnetism, but we'll make it interesting. We'll make a way out. We'll try to find a way such that this chapter doesn't pose that of a threat to us. So let's understand that. So in this chapter of geometrical optics or ray optics, these two terms are synonymous to each other. We treat light as ray, and there's a property of light known as rectilinear propagation of light. What does the property mean? Rectilinear propagation of light means that light ray travels in straight line. Rectilinear propagation of light. Just rectilinear propagation would suit our purpose or suit ourselves. So light ray travels always in straight line. If they don't see or observe, or rather come in front of an obstacle. And what happens is, light essentially can travel in all kinds of media. Light is unaffected by whether there's a media or not, because light essentially is an electromagnetic wave, which will come to it in the next chapter of wave optics. We'll read why light is of a dual nature, why light can act as wave as well as particle. So light over here is a wave and a particle both, and I'm treating the straight line motion. So in medium 1, medium 2, medium 3, or rather in all the media, what happens is, my ray of light would always travel in a straight line, and I can find the speed of light in all the media. In vacuum, the speed of light is equal to c, which is 3 into 10 to the power 8 meter per second. But the moment you change the medium, even the speed of light changes. And there's a property of medium, optical property of medium, all the media essentially, that is known as refractive index mu. Mu is refractive index. We'll come to refractive index, what exactly this thing is, but right now it would just suffice us to understand a thing about refractive index. This gives me the velocity of light in that medium. So velocity of light in a medium, I can just subscript a media over here, V medium is equal to C upon mu of the medium, or refractive index of the medium. Now, as per this definition, I'll understand that mu of vacuum has to be 0, which makes perfect sense, because this is in relation to vacuum, how high or how low it would be compared to vacuum. So mu of vacuum is equal to is equal to 1. So mu of vacuum is 1, and this means that in all the medium, or rather all the media to be more correct, I'll have different velocity of, or rather different speed of light. Let's say I change my medium, or rather I change my media from medium 1 to medium 2. What happens is, we have observed that if let's say this is medium 1, and this is medium 2, and this is the interface, or rather surface separating both the media. This is my interface. So when a ray of light meets the interface, two things can happen, or rather two things always happen. One of them is reflection and the other is refraction. What exactly is reflection? Reflection means a ray of light comes and returns back to the same medium. I mean, the interface doesn't allow the ray of light to go to the different medium or the next medium. This is your reflection. This is my reflection. But this ray can also move to medium 2. It can go from 1 to 2, 2. And that is your refraction. What happens is, if this medium 2 was not here, if it was whole medium 1, then my ray would have followed this dashed line. This would have been my original path of my ray. But because of refraction, what happens is, it won't be this path. It can take two paths. Either it would get deviated along this direction or in this direction. And both of the things are possible. It totally depends on how medium 1, medium 2 are related to each other. This is refraction. This is your, when medium 1, 2 are both present in light, or rather the opposite way, light is present in both the media, then I can say this is refraction. So whenever a ray of light meets an interface, the surface separating two media, my ray of light can suffer reflection or refraction. In this chapter, what we would be doing is, we'll start with reflection thing first and ignore refraction, and then later stages we'll ignore reflection and study refraction, and then we'll mix reflection, refraction both, and then study them together. Okay, so now let's start with the reflection thing. To wipe out the refraction, I can apply a technique. What I can do is, I can polish the surface or silver the surface. That would wipe out the refraction thing, because that won't allow the light to move from 1 to 2. And if I do that, that gives you something known as a plane mirror. See, so what I'm doing for plane mirror is valid always for reflection, and what I'm teaching right now is reflection and plane mirror both together, clubbed together. What I've done is I have removed refraction, so I'm studying only reflection by the help of a plane mirror. So let's say this is your plane mirror. This dashed thing over here gives you the idea that this is silvered or polished in the back side. So a ray of light cannot cross over to the other side. So let's say a ray of light comes over here like this. Now this ray is also known as incident ray, which comes to the plane mirror. This is your incident ray. So when it meets this interface, it gets reflected. And I can also draw a new ray over here. This is a line, you can say it a ray, whatever you prefer. This is known as normal. And this is perpendicular to the interface or the mirror at the point where the ray of light is intersecting the mirror. And this is reflected in this path. And this ray is known as, quite obviously, a reflected ray. As the name suggests, this is reflection. So you have incident ray, you have reflected ray, you have a normal. And angle between the normal and the incident ray is known as angle of incidence, denoted as I, and angle between the normal and reflected ray is denoted as R, angle of reflection. So my first law of reflection states that I is equal to R. Angle of incidence is equal to angle of reflection. I can just write it over in words also. Angle of incidence. Sometimes it is also known as angle, incident angle, which makes the same idea, is equal to angle of reflection. There's a need of a second law too. What is that? Second law states normal, incident ray and reflected ray all lie in the same plane. I'll write that for you. Second law of reflection. This states that normal, incident ray and reflected ray lie in the same plane. Why is this important? By now you must have realized that I equal to R doesn't fix my direction of reflected ray. Why? Because if I is equal to R, I can have n number of possibilities. This reflected ray could be in this way, could be behind the surface, could be at any angle. Essentially what could happen is, if you have a cone, right? If you take two lines on a cone, the two lines on that cone, or rather the lines to the surface of that cone, could have the same angle making with the axis. Which means the reflected ray is not fixed, is not defined if I have an incident ray. But the moment I say that the reflected ray must lie in the same plane as normal and incident ray, I have fixed reflected ray. So I now know where reflected ray would be going to, which path would it be following. So now I have fixed reflection completely. And these two laws of reflection tells you every story about reflection, all the things which you're going to read now about reflection. And this we have done for a plane mirror. This is sometimes known as, or rather every time known as, a plane mirror, because the geometry of this is like a plane. That's why plane mirror. Now over here, there's a talk about image formation. What exactly is image formation? Your body, any object for that matter, a pen or a duster, reflects or rather gives out a lot of light. And that light, when fall on your eyes, so when that light fall on your eyes, you're able to distinguish from where exactly this light is coming from. And then your brain interprets those light signals and processes that information and gives you that image. And then interpret what exactly this object is and from where this light is coming from. So for image formation, I need rays of light and they have to intersect. And at the intersection, I'll have the image of the object. Now the intersection, if it's happening on its own, which means the rays of light are meeting on their own, then I have a real image. But if they're not meeting on their own and I'm using geometrical construction, I'm doing it deliberately, then it is a virtual image. So real image is formed when the reflected rays are actually meeting at a point. But virtual image is formed when the reflected rays are not meeting at a point. We are deliberately constructing something, or rather doing a geometrical construction in a way that my reflected rays meet at a point. And that is thing which is not obvious a lot of times, but it makes sense when you start doing it. It might be very new to you, but it's not that difficult to. So let's bear with this idea that there's something called real image, something called virtual image. Real image is formed when there's actual intersection of rays, and virtual image is formed when I have deliberately done something to the geometry of the rays to meet those rays, make those rays meet at a point. That's virtual image. So for the case of plane mirror, this is your plane mirror, right? If I draw a perpendicular line to this plane mirror, this becomes my normal. If there is an object situated over here, basically I have constructed the normal taking object as one of the points, or the normal has to pass this object. This is my object. Now I know that I can make out any number of rays from this object, because a point object, or rather any object, gives out n number of rays, ray of lights. So a ray of light traveling in this direction. So a ray of light traveling in this direction would meet the mirror normally. And if the ray of light is meeting normally, this is known as normal incidence. And whenever I have a normal incidence, this implies I is equal to 0 degree or radian. Why? Because angle with the normal which the incident ray makes is your I, and here that angle is 0. I am making new angle with it. So if your I is 0, your R has to be 0 also, which means that my reflected ray would be just retracing that path. So for normal incidence, what I have is it retraces its path. It retraces the path. And this is also known as principle of reversibility. This thing over here, for normal incidence, your path is retraced. This is sometimes known as principle of reversibility. I'll write that for you. Principle of reversibility. Now, there could be another ray coming out of this object. Let that ray be in this very direction. Now, this is the point where this ray is meeting the mirror. I can draw a new normal over here, like this dashed thing. And this is my angle of incidence. It would be reflected in this path now. And this would be your angle of reflection. And by all logic, I know I is equal to R. So I can just write I is equal to R is equal to some angle theta. Now these two rays over here, these two guys, these two reflected rays are actually not meeting, which means that there is no real image formation, because all the discussion which we have been having in the previous talk on real image and virtual image was that the reflected rays must meet at a point. And here I know that these two rays are never gonna meet, which means I'll have a virtual image if I do some kind of deliberate geometrical construction. And how do I do that? If I take this ray backwards, and even this guy backward, this is where they would come from. Look, as they're coming from this point. And this is like the virtual intersection. And this I over here is your virtual image. So I can just write it over here, virtual image. We'll come to the real image formation also gradually, but in this instance we have a virtual image. So let's just bear through this. Now I know that this angle of here R, which is theta, would be equal to this angle theta, vertically opposite angles. Now this angle is theta, so this angle is also theta, and if this angle is theta, this angle is also theta. Alternate angles. Now this angle would be 90 minus theta, and this would also be 90 minus theta. This is 90, this is 90. So in these two triangles, in this one and in this one, all the three corresponding angles are same. This equal to this, this equal to this, this equal to this. And there's a common side over here, this guy over here, which is common to both of them, which means that these two triangles are congruent. Just figure out the congruency property, but I don't want to get into those detailed mathematical reasoning, because to me it is very obvious that if two triangles are similar and one of the sides are same, it means congruency. It is speaking itself that it is congruent, the triangles are congruent. So if these two triangles are congruent by CPCT, or congruent paths of congruent triangles are congruent, I can say that this length over here and this length over here are same, just label it as some P. This point where this incident ray is meeting the mirror, this normal incidence thing. So PO guy would be equal to PI, which means that the separation of object from the mirror is equal to the separation of the image from the mirror, and this thing is also known as object distance is equal to image distance. Object distance is equal to I hope this makes sense because it's a very basic mathematics. You might be reading this or might have read this in your previous classes in class 9 and 10 probably. So this is a diagram for image formation of a plane mirror, and this gives you a virtual image which is at the same separation from the mirror as the object was, which in other words is object distance is equal to image distance.